So Chebyshev's rule can feel overwhelming when you look at that formula. It's pretty gnarly looking, and those bullet points above. So here's just a quick video to talk to you about what it really means and how we're going to leverage it later. We're going to look back at our Lego price data for those Star Wars Lego sets because it's a good distribution in terms of not being normally distributed. When we looked at the box plot, we saw several high outliers, and looking here at this histogram, we can see we have a lot of right skew. This is an extremely right skewed distribution. So Chebyshev's rule, it allows us when we are dealing with maybe a distribution we can't see like that, or we don't have the raw data set, but we have been reported out our um, our raw, our summary statistics. It's really common that we get the mean and standard deviation given to us when we're reading through a paper or we're just getting information on the internet, right? Although a lot of times they will not give you standard deviation, but that is just a bad reporting choice. But if we have the mean and standard deviation, we can actually say a lot about what sort of typical values would look like. So I'm going to go ahead and grab the mean and standard deviation for our Star Wars Lego prices. We have this mean and standard deviation here. We also got variance, but I don't care. And we're going to talk about that calculation. So that calculation for Chebyshev's rule told us that the percent of data that falls within a certain number of standard deviations of the mean is going to be 100 times 1 minus k squared, 1 over k squared, percent. So we see this in the bullet points above. We start talking about 2 standard deviations because 2 is a pretty standard cutoff for what we consider unusual when we talk later about z-scores. So just to see what that means, if we're talking about 2 standard deviations, we'll see the calculation of the mean. That means that our k is equal to 2. So this formula would look like this. 100 times 1 minus 1 over 2 squared percent. And okay, well, let's just work this out. 1 over 2 squared is 1 over 4. 1 minus that is, well, 0.75, right? Because that's a quarter. And we still have our 100. We still have our percent symbol. So this is where that 75% number came in those bullet points above, simply from here. We could even redo this same exact work with 3 standard deviations, which is a pretty typical cutoff for an outlier when you're using z-scores. Again, we'll talk about those in a sec. But 3 standard deviations, just thinking about writing, we'd have 100 minus 1 over 3 squared percent. So this is 1 minus 1 over 9. All right, that's 8 over 9, which is, bust out a calculator, 0.8 repeating. So this is basically 89%. So within 3 standard deviations, we're guaranteed at least 89%. Within 2 standard deviations, 75%. So let's go ahead and see what this will look like with our Lego data. Basically recreate those bullet points up above, but with real data that we can go and check that this actually worked out. So again, we're talking about being within 2 standard deviations of the mean. So we're thinking of the mean. Come on. My Surface has not been this bad in a long time at responding to my stuff. All right. So we're thinking about this. The mean and within means that we're doing plus or minus 2 standard deviations. This is actually going to be a really common sort of formula and structure that we'll use later in the course when we start doing some inferential statistics with our confidence intervals. So we have a mean of, I'm going to go ahead and round because it'll be a close enough, of 60.63 and our standard deviation of 85.54. So if we do the subtraction first, we get 60 minus 2 85s. Not surprisingly, ends up with a negative value. And if we add 2 standard deviations, we end up with 231.71. So essentially, what we know from Chebyshev's rule is that 75% of the Lego Star Wars sets in that data set should fall between $0, because really there's no such thing as a negative $100 Lego set. They're not paying me to take Legos, to $231. So let's go ahead and check that out. Let's see if we get 75%, at least 75%. So let me bring back our Lego data so we can check it out. There's probably a clever way to do this, but I'm going to go ahead and just make a table because I'm going to sum up all of these things. You'll see right here I have all the Star Wars and all the prices, and I don't want to count them. I don't want to think too hard about it. Let me actually look back at that histogram and see. Actually, this is perfect. If I wanted to, I could just be like, how many are here and here? That's 112. And how many do we have? Out of 115. I got lucky here on my histogram. Um, my histogram has, oh, she's behind. Uh, the cutoff here, we don't have another value until 300. So I know that 271 is not going to be a problem in terms of using these two bars in my histogram. But that's just me being lucky. Here's another way to do this. Let me clear out all this pink highlighted stuff. If I wanted to, I could come in here and do a table. A frequency table just counts things up. It's a little bit weird to do with a quantitative or numeric variable, but it can still work. So I'm going to do price. I have to tell it to use the Star Wars Legos only. And I'm going to tell it to bin numeric values because price is not categorical. Normally, this would just tally up a categorical variable for me. But unfortunately, price is numeric. And so, in fact, actually, let me not bin it and show you how horrible this would be. Yeah, it shows you that there was 1, 399, 1, 499, 12. This is just a lot, a lot. I don't know how there's a bunch of NAs. I'm questioning why we have missing values, but it's okay. So I'm going to change this, and I'm going to say bin. That's basically asking it to act like a histogram. I'm going to have it start at 0, and it's a little silly, but I'm going to have it bin until I get to 271, oh, 231, 71. This will basically make my first bin all the things I'm interested in. So it should tally up everything that costs from 0 to $231.71. So if I press this compute, I get out this lovely table, which shows me exactly what I saw when I grabbed my whatever that was called, histogram bars, right? 112. And the nice thing is here, it even gives a relative frequency as one of the defaults. So there's a 94% of my Lego Star Wars stuff. Oops. 94% of my Lego Star Wars stuff ended up in that range, where we were guaranteed 75% by Chebyshev's rule. So that's Chebyshev's rule in action. So you can see if you really wanted to know more about it. And then again, this is super helpful when we get to z-scores and sort of why they matter and how we can really apply them even in cases where our original distribution is not normally distributed.